Hello. So I've just started the recording, and we'll be talking a little bit about multi-level models. Before the class started, I was mentioning a little bit about the reading. The reading says that in this next chunk, you should be reading from data analysis and regression modeling. You should be reading chapter 11 and 12 to 12.5. Now, chapter 11 is all about sort of the theory of multi-level models, and chapter 12 is kind of like practice of multi-level models. So if you find 11 a little too abstract to be useful, I would move to 12. I think normally what I might have done is just tell you to read chapter 12 and maybe skip chapter 11. But I think I included multi-level modeling chapter 11 as a kind of a generic recommendation because it explains some of the main concepts, especially figure 11.1. So today, I'm basically going to be lecturing through chapter 11 to get us kind of towards the applied knowledge covered in chapter 12. But today we'll really be talking about the theory and rationale behind multi-level modeling. Does anybody have any questions at the moment about this next chunk of the course? I'm hearing no questions, so that's good. Oh yeah, also I intended to circulate a survey about the final chunk of the course, about what topic you might want it to be on, so I could kind of construct the material and lead that. I haven't done that yet, and I know I haven't done it yet. It's been a kind of wild Thursday and Friday, and this week is also quite busy for me. I will try and get that survey out today, and then you'll be able to respond to it for a full week unless I get a full set of responses quickly. So the survey will be published hopefully today. Okay, accepting no questions and seeing none in the chat, I'm going to move on to talk a little bit about multi-level models, their theory, and their practice. So, last week, we talked a lot about models had a very particular form. And generally speaking, these models are all linear models of some kind, and they could be linear in a special transformed space, like linear in terms of the log odds of a probability. They could be linear directly in terms of a probability. If you did the reading, you saw that you can have linear regressions on counts if you treat them in a special manner. And finally, you can just have straightforward linear regression on a continuous outcome, like you've been doing since you started doing regression. Today, I'd like to talk about the simplest case that we've seen before, where you have an outcome y for observation I being modeled as a simple linear function of alpha plus x beta plus our error term. Okay, so the classic model, this is going to bug me until I fix it. The classic model has these components. And if I draw a scatter plot of what the regression looks like, I'm going to get a regression line. It continues to infinity. And I'm generally going to have this distance there, the point where the line crosses the y-axis, that is the alpha, and the slope of the line, sometimes you guys call this the gradient of the line, that gradient for a single unit change in x, resulting in a beta change in y, gives us the slope of the line. And this is a fairly standard linear regression. Now, in the last assignment, we fit a very special kind of model. And that model, I called it the fixed effect model. And that fixed effect model had unique means for every group. So in one of those examples, my model looked like this. Waiting time in a pub is equal to, and then I drew this little case diagram, and if I was in the Gallimaufry, I had a specific intercept, and I called that alpha G. And if I was instead in the Berkeley, I had a different intercept, alpha B. Okay? And finally, if I was in the milk thistle, I had a third intercept, alpha M. And then, just like before, I had a little error term. Okay? So we did this last week. In the workbook, you can see it. You also did this in terms of the years, predicting prices for houses. And this model is slightly different than our classical linear regression. We only have an intercept and an error term. So if I mark off points on the x-axis that pertain to the category of x, if this is the galley, this is the Berkeley, and this is the milk thistle, then my model just consists of a line that covers all of the points in the galley and then jumps to the point for the next line and then jumps to the point for the next line. And I can shift around the order of these categories all I want, and that changes the order in which we hit alpha G, alpha B, and alpha M, but it's still just a constant prediction over every observation inside of each group. And each group is treated differently. Then, when we did our linear probability model, we had a different model. It was still a fixed effect model, but this time we had a second variable. This time we had a slope that was whether or not we were waiting, or that was the waiting time at a particular pub. So let's write waiting here so you know that that's waiting. So this was the waiting variable. And our outcome was binary in this case, but we'll just call it y still. Okay? Does everybody remember that? We fit this model. And I showed you in the same kind of language that it existed in this fashion. And what you ended up having were 3 lines. There was one line, and then another line, and then another line. And each of these lines extended to infinity, just like before. But this distance was alpha g. This distance was alpha b, let's say. And finally, this distance was alpha m. And remember that we can rearrange this model into a contrast model that might express these intercepts differently. But the main point is, yes, this is the fixed effect model, Emily. So we could re-express this model in a different way, but we're still fitting the same slopes. For instance, if we were to do it in terms of a contrast model, we would get the intercept alpha. You'd get the contrast C Berkeley, and then you'd get the next contrast C milk thistle. They're substantively the same thing. So here, I'd just like you to focus on the fixed effect expression, which just gives us directly the alpha. Okay? So we're just going to work with the fixed effect expression. We want to fit different conditional means for each group. And in the assignment, we did this on an unstandardized weighting variable. So each of these represents the baseline of y when x is 0. So they're no longer just the mean waiting time in each group. They're a conditional expectation. Okay? Does everybody remember this from last week? We had 3 lines. And yeah, y was binary, but that's not the point right now. The point is that we had 3 lines, same slope. Each of these has the same gradient. They're parallel lines. But their intercepts are different. This is what happens when you fit a fixed effect model. You get multiple lines with the same intercept, or sorry, with different intercepts, but the same slope. Fitting each group as if it's got its own conditional mean. And in the workbook, we did this when on raw x variables, on raw waiting times, so we didn't do any kind of standardization or anything like that. Okay? So this is useful when you have different groups. And those groups might all experience the same gradient in terms of their x variables, but may start off in different places. So the theory that I gave you in the workbook was that your friend kind of had to put a premium on the ambiance of a particular place. That if they were in the milk thistle, they'd be, on average, more patient for the same weight. That's how you express that model. Each group has a different baseline. For the same weight, your friend might be more patient in the milk thistle than in the Berkeley. So this is the same, but the baseline is different. Does that make sense to everybody? Conditional on my x, this average, or this intercept, conditional mean, it's sometimes called, is different. The intercept is baseline. Yeah, I say baseline when I say intercept, because it tells you what value you have when x is 0. Alternatively, it's very common to re-express your x variable in terms of its mean-centered version. So you basically center it on 0, and then that tells you the baseline y when x is at its mean. But both ways, it's a way of kind of expressing what's the typical response, or sort of like what's your basic expectation when x is 0. And that's why I use baseline. Okay, so you all saw that fixed effect model. You fit it before. This is not new news. I'm just belaboring this point pretty heavily. Okay? Now, there's another kind of model that you can fit. On the graph, they have different intercepts. Is this what you were saying? Yes. So you see here, each alpha is different. And what I'm saying is, my prediction of whether or not a weight is too long in the workbook is going to be alpha g plus the amount of time I wait times beta if I'm in the Gallimaufry. But if I'm in the Berkeley, it's going to be alpha b plus my waiting time times beta. So the alphas are different. The intercepts are different, and that's what happens up here. You have 3 parallel lines. Same gradient, different intercepts. Okay. So one way that we can represent the fixed effect model is using additional subscripts, right? So I is equal to 1, 2, all the way up to the number of observations that we have. So this is the number of rows in our tidy data frame that we're doing the regression on. And if I want to get away from using that kind of big, verbose, case-based notation of in group 1, I do this, in group 2, I do this, in group 3, I do this. If I want to get away from that really verbose way of spelling a model, I'm going to use a different index. J is going to stand for 1, 2, n groups. So that's the number of groups that I have. And to distinguish that, I'm going to call this the number of observations. So J is going to be the index that we use to denote a group. Okay? So in our last example with the pubs, there are 3 pubs. That means J can be 1, 2, or 3. There were 17, if I remember correctly, or maybe 14. There were 17, let's say, measurements. So the number of observations, whoops, was 17. In this case, I can actually spell the fixed effect model by adding a j to my alpha. So this, now the last little bit is Gelman, this book, the Applied Regression Modeling, uses something a little bit additional to really drive this home. So the Gelman book uses this J bracket I notation to mean the J that I falls in. So in the Gelman reading, you would read this as the group that I falls in, the group of I. And he does this because it's like, you know, like in R, if I put the number of the observation, that's kind of like the I there. In this case, J would be some big old vector that contains all of the group numbers that I can be in. So for the 10th observation, you would get its group. So that's how the Gelman reading is going to represent group membership. So let's just get used to seeing that now. So again, you read this as the group that I is in, or I's group. I is the number of observations from the overall data set. So basically, like what Gelman is saying is that you might have like a vector called J in R that is, you know, it's the first observation is in group 1, the second observation is in group 1, the third observation is in group 1, the 7th observation is in group 2, the 8th observation is in group 2, and then maybe the 10th observation is in group 3, the 11th observation is in group 3. And then if I want to get the group of observation 5, that's what I'm getting. So it's just a notational thing. It's, you know, the group pertaining to the observation in brackets. It's just a spelling thing. It's something Gelman is doing to make it easier for you to read. Other kinds of sources don't use that language. They just put J and implicitly have that, oh, this J is actually referring to I. Okay, but we'll use the Gelman notation because you'll see it in the reading. So this is just a different way to spell the fixed effect model. This is still the fixed effect model. Now, as we saw in the last example, again, I'm going to kind of remove X for now, and we'll just talk about when we have an intercept and an error term. One of the problems that I mentioned with this model is that if I have a new group, I don't really have a good idea what my prediction is going to be. So if I have 3 groups and my regression line looks like this, right? So if I'm in group 1, I have that value. If I'm in group 2, I have that value. And if I'm in group 3, I have that value. This might be alpha 1, alpha 2, and alpha 3. Okay. What if I want to make predictions about some new 4th group? What do I do? Well, group numbers are arbitrary, so I could shuffle these lines around And there's no real meaning or intrinsic kind of understanding that, you know, A3 should continue on into group 4. Some of you might suggest, well, why not just use the average to predict group 4? And that's very interesting because our model doesn't actually have anything to do with the global average. There's no kind of definition or intrinsic expression for what the global average is. It just sees all the groups differently. The other model that we could fit, which I'm going to call, Sophie, I took x beta out because we're just talking about a model right now that has an intercept. It's simpler this way. If I throw in x beta, it'll be a little bit more confusing. So we'll get there, but right now I'm just talking about a model with an intercept. We'll get to the point where there's a beta as well, and I'll show you what that looks like in a second. So this is in contrast to what we might call the constant model, which would have y is equal to the mean of everybody plus the error term. And this regression line I'm going to draw in blue. And that might be just like the single flat line there. So I can either fit this fixed effect model, or I can fit that constant model. But in order for me to relate the two together, I need some additional thinking about how each of my groups relates to the global or constant overall mean. So I need some structure that tells us, okay, I've got these different groups, but across all the groups, they're related to this kind of overall or grand mean. And in statistics, the term that they've used for that is hierarchy. So it's how levels, whoops, that's not how you spell level, of your model relate to one another. So I can fit this constant model using something in R like, you know, y tilde 1. And I can fit this fixed effect model, which would be something like y tilde group plus 0. But I can't give kind of any way for the model to relate the two factors together. They just are different models. So if we use a hierarchy, we might come up with something like this. I might be able to say, okay, well, my observation is going to be modeled as it's kind of a group mean and an error term. But then I expect those group means, sorry, let's use the same color. Those group means to all be distributed around some global constant. Here I'm going to write it as A. Oh, that's not what I meant to do. Here I'm going to write it as A. with some additional upper level error. This is a hierarchical model. It's called a hierarchical model because this term here is given a secondary model in that next line. So this is like level 1, and this is level 2. Does everybody see that? I've now got 2 models. I've got what's sometimes called a response model, which is comes from the fact that we sometimes call Y our response. And then I've got a group model. And how are they related? Well, this way. So my group means are expected to be distributed around some kind of global mean, and then each group also has a random deviation from that mean. So it's like you're treating the group mean itself as a kind of outcome. Does everybody see that? A hierarchical model is just a model that has models inside of it. Like a nesting Russian doll, we put a model on each level. Okay? Now, the crazy thing is, we can substitute these two in for one another. So I get a model that overall looks like this. I get a global mean. Then I get a group level random deviation from that overall mean. And finally, I get my individual observation level error. This is easy to break down, global, group, and, oops, wrong color, local. That's a U. But you can use V, I don't mind what symbol you use. Usually I use E for my lower level error and a U for my upper level error. Cool. So a hierarchical model is just a model that nests another model inside of it. At least one model, that's okay. We also call this a multi-level model because it has, surprise, surprise, multiple levels. In our diagram up here, this means that we would replace something like our overall. Sorry, someone has their mic on or something? Anyway, we would replace our overall with the global mean, A, and then our kind of group customization is UJ. So this distance here becomes U1. This distance here becomes U2. And this teeny little one there becomes U3. In this model, if I want to know the prediction in group 4, it's just A. I don't have any special information about the group, so I just predict that it's going to be A. But I've done so in a manner that is consistent. A and U, that is, the global mean and our group predictions, have a structural relationship. In my model, they're treated as distinct terms. Now, this is where things get fun. In my group model, Uj is an error term. Patrick asks, so the global mean, blue A, is the mean of the local means, green A. Nope. It will depend on the variance of the groups. We'll get there. We'll get to kind of how this all relates to one another in a second. If we have enough time, I'd like to get to it today. If not, it's in the reading. In equation 12.1, page 253. So we might not be able to get to deriving that right now, but it's on page 253 of the Gelman reading. This is how we get there. Patrick, what is the case is that A plus Uj is alpha J. So this group estimate comes from U plus A for that group. So where this becomes interesting statistically is because this is a linear regression. It's a linear regression on a parameter that we don't observe, the group mean. Now we could just use an empirical mean, but we don't actually observe that technically in the data. We just observe y. So you remember how in the generalized linear model, we focus on modeling the log odds of y, even though we don't see the log odds of y. A multi-level model is kind of similar. You're setting up a model for the unobserved stuff you don't know. You don't know the group estimate in general, but using the relationship between the group and the global, you can come up with some good guesses. This is a linear regression, so Uj is distributed normally with a mean of 0 and a variance of the upper level model. And like before, EI is distributed normally with a mean of 0 and a variance of the lower level model. So this means we have two variances, and in our final model, in this version here, we have two random terms. U, our group level error, and E, our local error. So if I can erase this definition of hierarchy here, we have two random components. Okay? The way to kind of think about this is that this is the between group variability. If I abstract my problem, I'll repeat that in a second, Emily. If I make my problem much more abstract, and I'm talking about this, actually, I don't need that second graph. If I'm just talking about U, I'm talking about how different each of the groups are on average. Then, if I'm talking about E, I'm talking about a within group variability. So inside of each group, I'm going to have a bunch of points that are distributed around the group mean. And then in the other group, I'm going to have a bunch of points distributed around a group mean. And then in the third group, I'm going to have a bunch of points distributed around the group mean. So E and its variance term, sigma E, that's a constructed value that kind of averages over all of the groups. And it's giving us a single number description of, generally speaking, how variable each group is. And sigma U is giving us an expression for how different the groups are themselves. Uj is the between group variability. It gives us a model for how distinct all the groups are. If sigma squared U is really big, then our groups are very different. At the same time, if sigma squared U is very small, then it means our groups are broadly the same and they're close to A. If sigma E, the within group variability, is very large, then we've got wide groups, extreme amounts of dispersion around the group average. Alternatively, if sigma squared E is very small, then we have narrow groups. They all tend to be kind of tightly clustered. Whoops. They all kind of are tightly clustered around the specific group mean. So does that make sense when we're talking about between group variability and within group variability? Between group describes the sort of differences between the groups, and within group variability describes how tightly our data points are clustered within the group. Hannah asks, UJs are just how the groups vary from the global mean. Well, for this A estimate of the global mean, yeah. For the context of the weighting data, what could the global mean considered to be potentially? Go ahead and say that that's the overall average waiting time for Bristol. So the issue here is that the way these two variances combine, the way that sigma U and sigma E work together, means that it's not the case that alpha j, whoops, that's quite small, that alpha j is just equal to the average of observations in group J that is not the case in the multi-level model. The reason why is this variability. Instead, when you go through the work and derive the actual estimator, you get a multi-level model's estimate of alpha j is equal to the number of observations in group J divided by the within group variance times the empirical mean of group J plus 1 over the between group variance of all the data divided by normalizing factor, which is just nj over sigma squared E plus 1 over sigma squared U. Okay, this is really complicated. It looks pretty intimidating. But I'd like to show you that it isn't really that complicated. So just for a moment, let's ignore this bottom part, because it's just a standardization factor. And we'll say that this is proportional to this gobbledygook on the right. So in a multi-level model, our estimate of a group is proportional to, is going to be a function of the size of the group the within group variability and the between group variability. That's what you need to know. Multi-level model estimates are driven by group size, within group variability, and between group variability. And this is just in the case of a single intercept with no continuous x, no slope. Just talking about that one expression here. Okay? So I'd like to focus in on that for the last little bit here, just to talk a little bit about how this works. Okay? So I'm gonna pop that off. Okay. Okay. So if our group is really big, then it's going to mean that its group mean becomes more important. In this case, if it's bigger, it's more important. So holding all things equal, bigger groups will be closer to their group mean in a multi-level model. And that's because there's more information about that group. We have more observations, so our model can be more certain about the estimate in that group. Instead of kind of blending things towards what we don't know, we stick with what we do know about the group. So imagine in group 4, we have no observations. That means this goes to 0, and we just make a guess that's proportional to the average of y. So that's how the multi-level model constructs guesses about groups we don't have. The group size, if you have a really big group, it means that our predictions are going to be really close to the group mean. If we have small groups, then my predictions are going to shrink away towards A. Likewise, if my within group variability is very large, then I'm dividing the group value by a bigger and bigger and bigger and bigger number. So that's going to get to 0. It's just going to disappear. As sigma squared E gets really, really, really big, our groups become too noisy to have any meaningful information. That means that our predictions will tend towards the global average. So just so this is a little bit clearer visually, I can't do that. So big groups are close to the group mean. If a problem is noisy within groups, we get close to the overall average of y. If our between group variability is really big, it means that our groups are increasingly different. So between group variability is sigma squared u. If that gets really, really big, it becomes easier to tell our groups apart because they get farther and farther away from the global estimate. So if groups are very different, we get estimates that are close to the group average. So you need to remember these kinds of 3 intuitions about a multi-level model. Really big groups generally just going to recover the value of the group mean. If our groups are really noisy in that they have really big dispersion, our predictions are going to tend to the global mean. If our groups are very different from one another, they have really different means, then our predictions are going to tend to the group's mean. So a multi-level model is blending information about group size, within group variability, and between group variability to come up with a more sophisticated guess about what averages and values we should make, what predictions we should make about our groups. If you do the reading, you'll see that in some cases, really teeny groups are just going to be discounted. If I have a group with a single observation, I might be able to make a better prediction if I am more conservative and focus on the global mean, because that single prediction could have been a really errant, noisy point. A fixed effect model is going to draw our estimate right at that point. A multi-level model is going to take into account the group size and discount information a little bit. Still going to include it, still going to be included, but it's going to shrink away. So in the example of the weighting data, we had 3 groups. And they all had waiting times. You know, one of them was like this, one of them was like this, and then the milk thistle had 4 observations. The multi-level model is going to fit a global mean, and instead of saying, okay, our prediction for this really noisy group is the group mean, the average waiting time in the milk thistle, it's actually going to pull that down to be closer to the original global mean estimate. So a multi-level model is going to shrink the fixed effect model towards the constant model. And in big groups, we're going to get approximately the same estimate, but in noisy groups, we're going to get very different estimates. In really small groups, we're going to get very different estimates. In problems where groups are very, very different, we're going to get approximately the group means back. So this is all just with intercepts. And the mathematics, because of the way these levels relate to one another, get a little complicated. Next time, I think on Thursday, we'll talk a little bit about the code, and then also some of the implications that happen when you deal with these in terms of slopes. Finally, my recommendation is to actually maybe start with chapter 12 rather than starting with chapter 11. Chapter 11 is just looking at kind of the theory of overall kind of multi-level models and why we use them. But chapter 12 is a little bit more about the mechanics and point of how multi-level models work. So my recommendation is to try the reading from 12 on. So on Thursday, we'll do a little bit more theory, not much, and then we'll talk a little bit about code. And then I don't intend to lecture too much on Thursdays normally. But at this point, I think we'll break.